We're going to continue section 3.4 by looking at several examples to assist you with your homework. So first we're going to look at this example. It's example C, the next example in our slide. Okay? And so notice we want to solve this log function. We have the difference of two log functions on this side. So we want to use our properties. And we have a property that says when we have one log minus another log with the same base, we can rewrite them as log base 6 as a quotient. And so we'll have 3x plus 14 divided by 5. And of course, this is equal to log base 6 of 2x. Now what do we notice is that we have the one-to-one property. We have one log with the same base equal to another log with the same base. And so these values are just equal to each other. So we have 3x plus 14 over 5 is equal to 2x. And then if we cross multiply, we'll have, of course, 3x plus 14 is equal to 10x. And then subtracting x from both sides and simplifying, we get x is equal to 2. So let's just see what's happening here. Why is it stuck? Sorry. So we use the quotient properties first, as we said, and then we say that we can use the one-to-one property. And the one-to-one property, I'm sorry that is going fast, would say that this is equal to this. And then simplifying both sides by cross multiplying, we get this here. And then our solution is x is equal to 2. Now, for this particular problem, notice that we do have a log. So we have to go back and look at this x is equal to 2. Plugging it in here, we'll have 2 times 3, which is 6. And added to 14, I get 20, so I can take the log of 20. And here, I can take the log of 4, and so we are okay. Lastly, we want to look at these 4 examples. So let's look at A, which is this problem here. So the first thing is we know we want to get it into some kind of standard form. And the standard form we want to get it into, since it's an exponential, is a to the x is equal to some y. So the first thing we need to do is to add 4 to both sides, and we get this equation here. Now we're still not in this form because we have a coefficient in front of our a, which is this 2. So we divide each side by 2, and we get this form here. Now, I have it in this form, a to the x is equal to y, but the base is 3, so we have to take log base 3 of both sides. Doing so, we notice that this side, this will cancel away, and it's just equal to the exponent by our rules. And so this side, I just simplified my 15 divided by 2 to 7.5. And now we're solving for t, so we can add 5 to both sides. So I have 5 plus log base 3 of 7.5. And then we want to divide everything by 2. So I have 5 halves plus 1 half of this here. Now keep in mind that when we're doing this, we don't want to leave anything in the form of log base 3. We want to use our change of base formula. So we can rewrite this as t is equal to, our 5 halves can remain the same, plus our 1 half. But we want to rewrite this log base 3 of 75, and we can write it as, say, the natural log of 7.5 divided by the natural log of 3. And this is how we're going to have our answers for the test. But if you're using your calculator and you want to test it out, you should get 3.417 once you plug this into your calculator. But for our sake, we're going to leave all our solutions in this form here. Now let's look at B. B was we noticed, possibly a quadratic equation. E to the 2x minus 3, e to the x plus 2. We notice that this e to the 2x actually can be rewritten as e to the x to b squared. And if we have e to the x to b squared, indeed, this is a quadratic equation. So we can factor it. And how can we factor it? We take our e to the x's first and write them in the front. And then we find the factors of a positive 2 that when added together equal negative 3, which is minus 2 and minus 1. And so now we can set each factor equal to 0. E to the x minus 2 is equal to 0, and e to the x minus 1 is equal to 0. We'll start with our first one here. And so if we add 2 to both sides, we get e to the x is equal to 2. Now it's in our standard form, but to get to our x, which is an exponent, we have to take the natural log of both sides. And of course, the natural log of e to the x is just x, and our other side is natural log of 2. We will leave our answers in this form for our exam, but if you want to check it out, you should get 0.692 on your calculator. Now let's move to our second factor. We add 1 to both sides, we have e to the x is equal to 1. And then take the natural log of both sides. We'll have x is equal to the natural log of 1, which we know already is 0. So we do want to simplify these forms, and we get the solutions of x is equal to natural log of 2 and x is equal to 0. And this is the form we would leave it in for our exam. Now we're going to look at C of our examples. So again, we want to get it in some kind of standard form. In this case, it would be log base a of x is equal to some y. So I notice that I have a 2 here. So I divide each side by 2 so that it can get it in the standard form. And I'm left with log base 5 of 3x is equal to 4 divided by 2 is just 2. Now I can use the property that if I take my a and raise it to the y, it should equal x. So I take my 5 and raise it to the 2, which is here, and it should equal this value here, which is 3x. Of course, 5 squared is 25 is equal to 3x, and then we solve for x, and we get x is equal to 25 thirds. And so again, keep in mind, we could have from this step here, we could have raised these sides to the 5 log base 5 of 3x is equal to 5 squared. And then this would have canceled, and I would have left with 3x is equal to 25, which is my next step anyway. So you can do it in either way. So now we're going to look at our last example, D, which is this equation here. Log of 5x plus log of x minus 1 is equal to 2. And so we notice on our left side, we have the sum of 2 logs, so we can bring them together because they have the same base. And so it becomes log of 5x times x minus 1 is equal to 2. And so now we notice we can use our rule again where we take our base, and our base happens to be 10, which is understood, raise it to the second power, and it should be equal to this product. So I've multiplied that through. 5x times x is x squared, and then 5x times a negative 1 is a negative 5x. And so that we can solve this quadratic, I do, of course, 10 squared is equal to 100, and I subtract it from both sides, and I'm left with this equation here. I notice I have a 5 in common, and it makes life a little easier for us, so I factor out a 5. And then when I factor out a 5, I can divide each side by 5. And of course, the 5 goes away, and 0 divided by 5 is still 0, so I'm just left with x squared minus x minus 20 is equal to 0. Factoring, I get x minus 4, x minus 5 times x minus 4 is equal to 0. And setting them each equal to 0, I get x is equal to 5 and x is equal to negative 4. Now, for this particular problem, we have to worry about, because we have logs here, will both of these be solutions to my system? Okay. If I plug in a 5 here, I have log of 5 times 5, which is 25, and plug in a 5 here, I have a log of 4, so I'm okay. But let's plug in that negative 4. I'll have log of a negative 20, and then for my second, I have a log of a negative 4 minus 4, which is log of a negative 5. Now, we know that we cannot take logs of negative numbers, so these values do not exist. So what does that tell me about my solution? X is equal to 4. It tells me that it is an extraneous solution. And so therefore, the only solution to this problem is x is equal to 5. So keep in mind, when you're working these problems, anytime I have a log, I need to plug it back in to make sure I do not have what we call an extraneous solution. And an extraneous solution is a solution that looks like it might be a solution, but it actually gives values that do not exist.